Okay, guys, welcome back to the discussion on fields. Okay, and in this lecture, what we are going to do is to specifically talk about separable extensions, to be very specific. But actually, what we are going to talk about more is separable polynomials, and you will see that such a thing we have already done, to be honest. Okay, but rather let's exploit it once more. Okay. So what do we mean by a separable polynomial if I talk about that? So let me start with the definition, and the definition will be very relevant to you at the point when I will give. So let f be a polynomial over ft, then we say f is separable if there does not exist any extension of f over which f has repeated roots, and that's it. That's the definition. That is, in some sense, f does not admit any repeated root. We have already discussed such things, that if f is some field and I choose a polynomial over it, then the polynomial might not have the roots in f itself. So there always exists an extension. If not, then at least the algebraic closure of f, or let's say the splitting field of the polynomial ft, over which this will surely split into linear factors, and there we can attain the information about the roots. So in some sense, you want to talk about the existence of repeated roots, or not or no existence of repeated roots in the algebraic closure, to be very specific. But I am admitting that it cannot have any repeated root in any extension. In other sense, if I talk about in general, then the polynomial will admit no repeated roots, to be very specific. Getting my point? Okay, that's it. So that's basically the definition. And if I recall, then previously we have already discussed a lot about repeated roots, but rather let's exploit it once more, to be very specific, because I sometimes forget the things I have already done. So the notion of repeated roots, and I will do this a bit quick, but rather you will be able to recall. So what we were trying to do in the case of repeated roots, if you go for a quick recall, then what actually we are trying to do is to mimic the behavior of derivatives in case of the real analytic polynomials, right? We know that if I am talking in the real field, then the polynomials have repeated roots if the polynomial and its derivative share a root, right? Then that root becomes a repeated root. And furthermore, we know that over real fields, in an analytic sense, to be very honest, then all polynomials are differentiable, right? Are sort of entire on the real field. And the polynomials are sort of very important if I talk about the real analytic sense, because provided some restricted conditions, any continuous function is able to, we can approximate a continuous function in some sense in terms of polynomials. Rather than polynomials are very important to talk about, at least in the real analytic sense or in the complex analytic sense, whatever you want to talk about. But the notion which we want to mimic is the notion of derivatives related to the existence of repeated roots, right? So what we are going to do, so if f is a field, then we take ft, and we know that ft is an infinite dimensional vector space over f. This is something we know already. What is the basis of ft? We know that there is 1 t, t square, and so on. Now take a map from ft to ft, and let this be a linear transformation. This is something which we have already known if you have studied multivariable calculus. A playlist of multivariable calculus is available in this channel itself, where I have in details exploited the various notions of derivatives in terms of functions from Rn to Rm, where n and m are arbitrary. There we have seen that in general, derivatives are actually linear transformations. So this is some sort of relevant in this case as well. And we know that in case of linear transformations, the definition is done just as we define it on the basis elements. So what I do, I take a basis element and I define the map on the basis element to be n times t to the power n minus 1. So I guess you are getting already the point that we are actually mimicking the definition of derivatives of polynomials, right? Fine. And this is an easy verification that the addition of the derivative of the addition of two polynomials is the addition of the derivatives of the two polynomials. And actually it also satisfies the Leibniz rule of multiplication, that is, this is df times g plus f times dg. Okay, these are very easy verifications for every f and g over this field. Now, if you recall as a definition that the that ft in ft is said to have alpha as a repeated root. Okay, alpha as a repeated root in any field extension or the field itself or any other field extension in k over f, whatever you want to feel like, if t minus alpha square divides ft, right? Okay. And what we can claim from here immediately is that if f is a field and ft is a polynomial over f, then what I want to say is the following: then there does not exist an extension, or in other words, what I typically want to say is the following: then uh, the derivative of ft and I mean sorry, the GCD of ft and its derivative is 1 if and only if f has no repeated roots. F has no repeated roots. Okay, is it clear? And you can actually compare it to the real analytic sense. There we have seen that polynomials over real fields, they actually have repeated roots if the derivatives also share a root, right? Fine. So in simple sense, this is the case which we want to exploit, and the proof is typically very simple. The proof is actually very simple. Observe the following. We can just take this the proof is actually, yeah. So the proof, let's say let qt in ft be such that the degree of qt is greater than 1. Okay, is it clear? Is it clear? Then suppose the ideal generated by ft and its derivative is generated by qt. Since we are working over the PID, so we know that the usual definition of GCDs over PIDs is given by, it is generator of the principal ideal generated by two elements. That will give me the GCD of A and B. Right? This is something which we recall. Now suppose FT, the ideal generated by FT and DFT is QT, right? Then what can we conclude from here? Okay. Now let E be an extension where QT has a root. I guess this will do. Where QT has a root. Okay, fine. Let's say the root is alpha. Then what we can say? Then since qt divides ft, therefore alpha is also a root of ft. This implies that I can write ft as t minus alpha times gt, right? I can do this, which implies that the derivative of ft should be, by the Leibniz rule, this should be t minus alpha times the derivative of gt plus gt, right? But then derivative of f evaluated at alpha, this should give me g of alpha. Clear? Is it clear? What does this mean? Uh, yeah, so what do I want to conclude from here? Right. Now, yeah, but then qt divides dft as well, right? Since qt divides dft as well, this implies that the derivative evaluated alpha should also be 0. That is, alpha is also a root of the derivative. What does this imply? This implies that g of alpha must be 0, which implies that I can write g of t as some t minus alpha times h of t. But then my ft, what does it become? It becomes t minus alpha squared times h of t. What does this imply? That t minus alpha squared divides f of t. What does this imply? That ft has a repeated root. Right? Okay. So therefore, if the derivative is not equal to 1, therefore we can conclude that it has a repeated root in the field extension Et. Okay. And the converse part is also very trivial. Conversely, if there exists some alpha in a field extension E over F such that t minus alpha square divides f of t, then what I can do, I can write f of t as t minus alpha squared times gt. So I am explicitly writing it in et, right? I am trying to write it in et. But therefore the derivative will become 2 times t minus alpha gt plus t minus alpha squared the derivative of gt, which implies that so t minus alpha divides the derivative of ft as well, right? So what does this mean? This means that the GCD of ft and its derivative is not equal to 1 in et. In et, let's go back to the hypothesis. There we had talked about the GCD, but this GCD was being discussed about in ft. What we have reached a point where the derivative is non-trivial in et. But observe that the derivative, I mean the GCD actually from if a b equal to, let's say, d in f, then it extends over to some other field extension of f as well. The same GCD occurs there as well. Why is it so? Because from the usual definition of GCDs over PIDs, what we know is that, I think we have discussed in the previous also, but let's see. Because if AB is equals to this, then what do we know? Then I can write D as some A times F plus some B times G, right? But what does that mean? This means that D is in the ideal generated by A and B in K as well, right? In K. Getting my point? Because the field F lies inside K, so all of these factors holds in K as well. And the converse is also true, right? Right? Because A can be written as D times S, B can be written as D times T. So all of these hold in K as well. Right? Because D, S, T here, F and G all lies in K because they lie in F. So GCD actually carries over to the field extension. So therefore, if the GCD of two elements is non-trivial, I mean not equal to 1 in some upper field, in some ambient field, then it must also be non-trivial in the lower lying field as well, right? Because if it is equal to 1 in the lower field, then it should be 1 in the upper field as well. So this implies that the GCD of ft times dft, I mean GCD of ft and dft is not equal to 1 in ft as well. And this concludes the proof. Recall, right? Getting my point? Yeah. So this was a simple discussion. You can just write out the rigorous proof, or you can just go back to the previous lecture where we had discussed about repeated roots. But fine. Getting my point? Right. Right. Yeah. So now this brings us to a very important sort of another important sort of a characterization of repeated roots, which is the following theorem, that if ft is a polynomial in over f, which is irreducible over f, then ft has repeated roots if and only if the derivative is 0, identically 0. Okay. Before moving on to the proof, something which we can immediately discuss from here is the following, that if the characteristic of the field is 0, then you can observe it immediately that the derivative is identically 0 if and only if the polynomial f is some constant polynomial over the field, hence a unit, assuming it to be a non-zero polynomial, so it's a unit, right? Therefore it is no more irreducible because it is a unit, so I can write it as a one time c in some sense like that. But rather than that is what I wanted to say. Therefore, what do we typically conclude from here is that if I have a irreducible polynomial over a characteristic field, I mean over a field of characteristic 0, then it cannot have a repeated root, right? So irreducible polynomials over fields of characteristic zeros cannot have repeated roots. But it is obviously possible in case of polynomials, or polynomials over a finite characteristic, right? Because um, for example, if I talk about this polynomial, for example, let's say let's say f of t is equal to 1 plus let's say x square plus x to the power 4 over, let's say, f2, okay, the field of characteristic 2, then what is the derivative of t? then this becomes 2x plus 4x cube, but this is modulo 0 over f2, this is modulo 0 over f2, so this is identically 0, while this is not a identically 0 polynomial. So this readily holds over finite fields, but not over fields of characteristic 0. And the proof is actually very simple. Proof, suppose if f is irreducible, then what happens? Then observe that the derivative, because we see if f is irreducible, then the only possible factors of f are either 1 or f itself, right? So therefore its GCD should either be 1 or ft, right? But the degree of dft by definition is strictly less than the degree of ft. What does this mean? That then the derivative should exactly equal, I mean the GCD of the polynomial and its derivative must exactly be equal to 1. Getting my point? And that brings us the proof, right? Clear? Getting my point? Fine. Clear? Okay, right. Yeah. So yeah, did I do it correct? I said that it is extremely simple, but did I do it correct? I wanted to prove f is irreducible, right? Yeah. So yeah, fine, no problem. Right, right, right. Yeah. So let's continue. Wait a second. Huh? Yeah. Fine. Okay. Right. So let's move on to the discussion of separable polynomials as we were doing, right? Separable polynomials, we started our discussion with separable polynomials, right? So let's continue. So we had previously given, in fact, the definition of a separable polynomial, that it has no, if it is not having repeated root in any field extension. That is exactly the definition of a separable polynomial, and this is something which we can immediately get from the whatever we discussed in case of repeated roots, that f is separable if and only if the GCD of f and its derivative is 1. Getting my point? Okay. Furthermore, we can also have this proposition in hand directly, that if, or rather let f be a polynomial over ft such that f is irreducible, then f is separable if and only if the derivative of f is identically 0. I mean not identically 0, right? Fine. Okay. And also the corollary which we have discussed also, that if the characteristic of field is f, I mean sorry, the characteristic of the field is 0, then every irreducible polynomial is uh, separable. It admits no repeated roots, as the derivative of the irreducible polynomial can never be 0. Identically, obviously identically. But we have seen this previously, that the derivative being identically 0 need not hold in case of uh, finite fields of finite characteristic, right? Okay. Right. So over finite characteristic field, there can be reducible polynomials which are not separable. Okay, fine. Never mind. Let us talk about a very important type of field, and this will bring us a number of observations, which are called perfect fields. So what is basically a perfect field? Let f be a field of characteristic P, obviously a prime, then f to f, phi is a map which takes A and maps it to a to the power P. Okay. Then this you can take as an exercise, that phi is a field homomorphism. Phi is a field homomorphism. As observed that if I take A plus B to the power P, which is the image of A plus B, then this is actually we can apply the binomial theorem, right? Because we are in a field, so it's commutative. So this is a to the power p, so on and so forth till b to the power p. All of the elements, in between are some multiples of p. So this is congruent to a to the power p plus b to the power p modulo p. Products they split immediately due to commutativity, and you can also check that this is actually equal to a to the power p inverse. Clear? These are very easy observations. This phi is called actually the Frobenius map of f, and this is also pretty easy to observe also, that the kernel of phi is an ideal in f, and since f is a field, the kernel can be either 0 or f. Okay. Now if it is f, then that means that phi is identically 0, which is not the case, which we can easily observe because phi of 1 is 1. Therefore the kernel of phi must be 0. What does it mean? That phi is injective. So phi is naturally injective. The Frobenius map is always injective. Now if f is a finite field, suppose f is a finite field and phi from f to f is the Frobenius map, right? Then phi is surjective as well, right? Surjective as well, because over phi, if there is a map between two fields of same cardinality which is injective, then that is naturally surjective. Surjective as well, as the cardinalities of f is finite, right? Getting my point? So this brings us to the definition. Now once it is surjective, so phi becomes bijective. It is also already a field homomorphism, so it actually becomes a isomorphism, right? So definition is the following, that f is said to be a perfect field if its Frobenius map is a surjection. If its Frobenius map phi is a surjection, that is phi is an isomorphism, or rather typically an automorphism, because we are over the domain and codomain are the same. It's an automorphism. Is it clear for everyone, the notion of Frobenius map? Okay. Now see the following. This is a very easy observation. That suppose f is an algebraically closed field, is an algebraically closed field of characteristic p. Okay. Then suppose I choose the Frobenius map from f to f, which takes a to the power p. Now suppose I choose that let b comes from f. Okay. Let b come from f. Then observe that, or rather, what can I actually claim from here? So if f is an algebraically closed field, then what do I know? That f is an algebraic extension over itself, right? So what can I say from there? Or then observe that if I take this x to the power p minus b from ft, then this has a root, okay, in f, right, due to f being algebraically closed, right? Therefore there exists some a in f such that a to the power p is equals to b, or phi of a is b. What does that mean? That means that phi is surjective. Getting my point? So what do we have? We have the algebraically closed field of a, so no, I, did I say, yeah, fine, right? So therefore if I have an algebraically closed field of characteristic p, then that field is perfect. Clear? Clear? Okay, fine. What more can we discuss in this context? Okay, we can actually discuss one more observation, one more important observation, which is the following. Um, Suppose f is a polynomial over ft, which is irreducible. Okay. Now suppose, or let me actually talk about this in terms of a theorem. And this is also a very important theorem regarding perfect fields in some sense. That if f is a perfect field, um, of characteristic, let's say p, or let it be just be a perfect field. Okay, I can also talk about the field of characteristic p in this case. Okay, then every irreducible polynomial is separable. Getting my point? So if f is a perfect field, then every irreducible polynomial is separable. Clear? Fine. Let's try and prove this. Suppose f is a polynomial over ft is irreducible. Okay. Suppose the derivative of f is 0. What do I mean by the derivative being 0? Because we are working in a field of characteristic p, the derivative being 0 means that f of t can be written as a naught plus a1 t to the power p, so on and so forth till a n t to the power, let's say np, right? So we are working in a field of characteristic p, so I should have mentioned that, right? Yeah, so the result actually was in my mind to talk about, but the hypothesis wasn't there. So I am actually talking about a field of characteristic p. Fine, is it clear for now? Right. But then, since f is perfect, for each of these ai's, there exists some bi in f due to surjectivity of the Frobenius map such that bi to the power p is equals to ai. Therefore, my ft becomes b0 to the power p plus b1 to the power p plus times t to the power p, so on and so forth till bn to the power p x to the power np. But actually observe that this is nothing but b naught till bn t to the power n whole to the power p by the binomial expansion. What does this mean? This means that f is not irreducible. Okay. So what did we start with? We started with that f is not separable, right? Because we had chosen that the derivative was 0. That is something which we started with. So we started with f being not separable. We proved that it's not irreducible. Hence, take the uh, contrapositive of this. What we will get, that if f is irreducible, then it needs to be separable. Yeah, getting my point. So what do we conclude from here is actually the following. Because we have previously seen that over fields of characteristic 0, irreducible polynomials cannot be, irreducible polynomials are separable. They cannot have repeated roots. So what do we conclude from here is the following corollary. If the characteristic of a field is 0 or the field is perfect of characteristic p, then any irreducible polynomial uh, f in ft is separable. So previously we had only observed that over fields of characteristic 0, irreducible polynomials have no repeated roots, that is irreducible polynomials are separable. But now we conclude something more, that if I also have a perfect field of characteristic p, still irreducible polynomials are separable. And now it's good time to introduce the notion of a separable extension, because we have discussed enough about separable polynomials. Let K over F be a field extension which is algebraic. Then we say that K over F is separable if and only if for every alpha in K, the minimal polynomial of alpha in F is separable. Yeah, so this is in F. Clear? So when do we say that an algebraic extension is separable? If for every element in K, the minimal polynomial of that element in F is separable. Clear? Clear? And therefore, in terms of separable extensions, with due respect to all the work which we have already done, this is actually a very easy consequence, that if the characteristic of F is 0 or F is perfect, and the characteristic of F is P, then any algebraic extension is separable. Why is it so? Because the minimal polynomial by definition is irreducible. So the minimal polynomial, since irreducible, and since we are working in a field of characteristic 0 or the field is perfect, therefore it is naturally having no repeated roots, with due respect to the previous coronary and the previous results which we have discussed, is separable. So this is one. Number two is that if the characteristic of the field is P is obviously a prime, then every algebraic extension is separable. Every algebraic extension is separable. Yeah, sorry. Then every algebraic extension is separable if and only if F is perfect. That is what I wanted to talk about. F is perfect. Clear? Fine. So we end this lecture here. I'm not sure whether I will be bringing any more lectures, because all the nice aspects of fields have already been covered, either in the ring theory course where we had discussed about finite fields previously, and the other aspects have been covered here. I might just come up with a very short lecture on talking about extensions being isomorphic. I mean an independent lecture on field extensions being isomorphic. Okay. So yeah. So meet you guys